Right. Okay. Just let me share my screen. Yeah, is it visible, the screen?
Yes.
Yes. Okay.
Yes, sir.
Okay.
Yes, sir.
Yeah. Okay. Actually, I'm not well today. Actually, I had my vaccination from the college, and I'm very feverish. Yesterday, the whole day I was suffering from fever, and today also I'm not feeling that well. Anyways, let us start. In the previous class, we had done till the error detection methods, right? And we had done 1D parity check, 2D parity check, as well as the checksum method, right? And today we will finish the error detection method. So one more is remaining, and that one is known as the cyclic redundancy check, or the CRC method. And after that, we will try and study one error correction method. And if I complete that in time, then we will start with the flow control as well. Okay. So as we all knew in the previous session, that there were four methods for error detection. One is 1D parity, 2D parity, checksum, and as well as CRC, that is the cyclic redundancy check. Now, what is CRC? Let us understand that unlike the checksum scheme, which is based on addition, CRC is based on binary division. So, if you remember the previous one, in the case of checksum, we were doing what? We were doing something called as ones complement addition, right? And what was the formula? If you remember, it was 0 plus 0 is equal to 0, 0 plus 1 equal to 1, 1 plus 0 equal to 1, 1 plus 1 was equal to 10, and 10 plus 1 was equal to 11, right? But that was based on addition. But in the case of CRC, we will be doing something called as binary division, or explicitly, if I want to say, we will be doing something called as uh, uh, it is known as modulo 2 division, right? Modulo 2 division. Now, what is modulo 2 division? We will come to that later. Okay. So, in the CRC, what happens is a sequence of redundant bits called the cyclic redundancy check bits are appended to the end of data, so that the resulting data unit becomes divisible by a generator, right? Now, again, what's a generator? What are cyclic redundancy check bits? We will all see them in the example, right? And at the destination, what happens is the incoming data unit is divided by the same number. So, again, a generator will be there that will divide the data at the sender side, and the same generator will be again given to the receiver, and the receiver again will divide the incoming message with the same generator that was generated by the sender. Okay. So, again we will see this in the example. Also, a remainder indicates, so whenever we are dividing at the receiver side, a remainder, right? If a remainder is set, which means a remainder is not all zeros, if there is one ones or two ones or three ones, okay, so a remainder indicates that the data unit has been damaged in transit and therefore must be rejected. Okay. So, again we will see in the example that if there is an error, what's the result? If there is no error, what's the result? We will see in the example. Okay. So, the example is given here, but again we will try and show this using our own example. Okay. So, just for a second, if I just present this, because I won't be able to write then. So, okay, I went to the college and I brought the pen tab actually. Just a second. Okay. Okay. So, we are studying what? CRC, right? Just pardon my handwriting. Just bear with that. So, CRC. Okay. So, before starting with CRC, first and foremost, we need to understand that in the checksum scenario, we said that we actually did something called as ones complement addition, right? But in this case, we will do something called as binary division, right? And I also said that the binary division can be known as what? Modulo 2 arithmetic, right? Now, what is this? Let us understand. It is nothing but a simple XOR operation. Now, if you remember the XOR operation, it was nothing but that if the bits were the same, so it was, if it was 0 and a 0, the result would be what? A 0. If it was, the bits were different, then the results would have been what? 1. right? And if the bits were again same, results would have been what? A 0. This is nothing but the modulo 2 arithmetic that we will follow, right? So this is the first thing. The second thing is we will have two things. First is the message, right? So let us see the previous example. What was the message? The message was suppose 1010 triple 0. Okay. So let us say that the message is 1010 and a triple 0. Okay. Second is we will have something called as the generator. Now what's the generator? Let us understand. Whenever we have a generator, now obviously we understand from the OSI model that whenever a data is being sent by one data link layer to the other data link layer, they will obviously follow some protocols, right? And using the same protocols, they will decide on a common generator. Okay. Now whenever a sender is trying to send data to the receiver, the data link layer of the sender and the data link layer of the receiver will communicate with each other before sending the data, that okay, this is the common generator that we need to follow. Okay. Now for example, if I say that the generator that they decide on is something called as x to the power 3 plus 1. Okay. Now if the generator is in the form of x to the power 3, x to the power 2, x to the power 1, we call this as what? A polynomial, right? Now how do we generate the data from this polynomial? Let us understand. So if I just draw, kindly excuse my handwriting, anyways, so if I draw this like this, and if I say this is 3, this is 2, this is 1 and this is a 0, right? So we can see if it is x to the power 3, so we have 1 into x to the power 3, right? We have 0 into x to the power 2, we have 0 into x to the power 1, and we have 1 into 1. Is it clear till now? Anyone, if you can tell me?
Yes, sir.
Okay.
Yes.
So if it is, if the value in 3 is set, we will say that this is a 1. If the value in 2 is not set, we can say this is a 0. If the value in 1 is not set, we can say this is a 0. And if the value in 0 is set, we can say this is a 1. So we can safely say that the generator, if it was in this form, is actually equivalent to what? 1001. Am I clear?
Yes, sir.
Okay. So in the question, it may.
Can you repeat?
Okay, okay. Let us say that whenever we had the data link layers sending data to each other, right, of the sender and the receiver, the sender and the receiver, before sending the data or before receiving the data, they decide on a common generator. Okay. Now the generator can be in the form of 1001, it can be in this form, or in your question it can be said that okay, the generator is in polynomial form and the form is nothing but x to the power 3 plus 1. Okay. Now how do we take this polynomial and we divide and we generate this 1001? Okay. So how do we do this? So let us say that this is x to the power 3, right? So if I just say that the numbers are 3, 2, 1 and 0, so if I just create a list like this, right, and we say that this is the third one, this is the second one, this is the first index, this is the 0th index. Okay. Now in the third index we can see that it is x to the power 3, so we can safely say that it is 1 into x to the power 3, right? We do not have x to the power 2, so we can say 0 into x to the power 2. We do not have x to the normal x or x to the power 1, so we can say 0 into x to the power 1, right? And we have a 1, which means we have 1 into 1. Okay. So if we have this, we can safely see that in the third index, since we have multiplied x to the power 3 by 1, we can say that the third index is actually set, right? So if it is set, we can say that for the third index it is a 1. Okay. For the second index, we can see that it is, we have multiplied by a 0, which means it is not set, right? So if it is not set, we can say that for the second index it is a 0, right? For the first index, again we can see that it is not set because it is multiplied by a 0. So again we can say that this is a 0, right? And for the last index, that is the 0th index, we can say that again it is set because it is multiplied by a 1, so we can safely say it is a 1, right? So again, if I have 1001, in this case we can safely say that the polynomial will represent 1001 as in the data. Am I clear, everyone?
Yes.
Okay.
Yes, sir.
Okay. Yeah. Now,
Yes, sir.
right. Okay. Now, there is one more thing to consider, that suppose if the generator is n bits long, right? So obviously till now we have seen in the examples that generally we are adding, or everything, error detection, error correction, is everything is based on the concept of redundancy bits. Okay, now obviously if I take redundancy bits in this case, we can say that the redundancy bits are, for example, will be equal to n minus 1, right? So in this scenario, if the generator is 4 bits long, so r in this case will be 4 minus 1 will be equal to what? 3, right? Now what is this 3? Which means we need to add 3 redundancy bits to the actual data, right? Now what are redundancy bits in this case? So at the sender side we will add nothing but 3 zeros to the actual data. Okay, now let us understand how. So just at the sender side, if I write it like this, so what was the actual data? It was 1 0 1 0 0 0 and a 0, right? Am I right till now? Okay, yes. And to this data, since the generator is of 4 bits long, so what we will do, we will add 3 zeros to the actual data. So again, which means we will add 1 2 and 3 zeros to the actual data. Okay, now what are these 3 zeros actually? If you just look at the first slide, we were saying that a sequence of redundant bits called the cyclic redundancy check bits. Okay, so these are nothing but the CRC bits that we are adding to the actual data. Okay, so just let me delete this. Okay, so this is the actual data that we will have. These are the 3 redundancy bits that have been added to the data, and what we will do is we will just divide this data with what? The generator, that is 1001. Okay, now obviously you need to understand that since this is 1001, so obviously it means that we will just multiply this generator every time by a 1, right? Why a 1? Let us understand, it will be very clear from the example itself. Okay, so if I multiply this with a 1, so obviously it will be what? 1001, right? Now what we will do, we will just do the modulo 2 arithmetic. What was the modulo 2 arithmetic? It was nothing but the XOR, right? So if I have 1 and a 0, it's a 1. If I have 0 and a 1, it's a 1. If I have 0 and a 0, it's a 0. If I have 1 and a 1, it's a 0. So am I clear till this?
Yes.
Okay.
Yes, sir.
Okay.
Yes, sir.
Okay, so as I said that this 1001, this is a generator, and again this will be multiplied by 1 every time. So which means if I need to multiply this with a 1, it will be 1001. So again these zeros will be excluded and we will start with a 1, right? Okay, now how do we start with a 1? So we have 1 and a 1. We need 4 bits, we have 2 bits. So what we will do, we will just take down this 0, okay, and we will take down what? This 0. Okay, so again if I multiply this with a 1, it will be 1001. Okay, so again 1 and 0 will be a 1, 0 and 0 will be 0, 1 and 0 will be 1, and again 1 and 1 will be a 0, right? So again the first bit is a 0, so obviously we need to delete this. The first bit needs to be a 1, right? Because we are always multiplying this with a 1.
Sir,
Tell me.
I mean, this is like the ordinary division that we do, but instead of base 10, we are doing in binary.
Exactly.
Right.
Exactly.
Okay, sir, but sir, I didn't get how. I mean, the first one, 1010 minus 1001.
Hmm.
Shouldn't it be only 01?
No, we are doing modulo 2 arithmetic in this case. And what is modulo 2 arithmetic? It follows the principle of XOR operation. That's it. We are not exactly doing the binary division, right? We are doing
Oh,
something
okay.
called as a modulo 2 arithmetic, and that is nothing
Okay,
but a
sir.
XOR operation. That's it.
Understood.
Okay, right. Now again we have 101. So obviously this needs to be a 4-bit number. So again what we will do, we will take down this 0, right? And again we will multiply this with a 1, so it will be 1001. Again we will do the XOR. So 1 and 0 will be what? A 1. 1 and 0 will be 1. 0 and 0 will be 0. 1 and 1 will be 0. So again we will remove this. Okay, and we will take down this 0, right, as well as we will take down this 0. Okay, so again we will multiply the generator with a 1, so it will be 1 0 0 and a 1, right? Okay, so again 1 and 0 is 1, 0 and 0 is 0, 1 and 0 is 1, and 1 and 1 is 0. So delete this. Okay, and lastly we have this 0, so we will have this 0, and again we will multiply generator with a 1, so it will be 1 0 0 1. So if I just XOR this, so 1 and 0 will be 1, 1 and 0 will be 1, 0 and 0 will be 0, and 1 and 0, 1 and 1 will be 0, right? But in this scenario we will not delete the preceding zeros. Why? Because since this is the result, and in the example we have seen that we have added what? 3 zeros, 3 redundant bits or 3 CRC bits, right? And since this is the result, what we will do is we will just remove 1, right, and we will retain 3 bits like this. Okay, and why do we retain these 3 bits? Because whenever this data will be sent to the receiver side, let us see what will happen. So the data will be 1010 000, and instead of these 3 zeros that we added when we started the division process, we will just add the remainder, right? And obviously the remainder is of should be of 3 bits. Why? Because we have added 3 CRC bits, so the remainder should be of what? 3 bits. So what we will do here, we will just add 0 1 1, right, like this. This will be done just to just to segregate the data and the CRC bits, and this data will be sent to the receiver side. Am I clear till this?
Sir,
Tell me.
sir, in this condition, if the result if we
Mhm.
get a 4-bit, so how we will put it in this?
You will never get a 4-bit. Try it. Okay. Okay. Right. Okay. Just a second. Okay. So at the receiver side, let us understand what happens. So what's the data? It is 1010 000 and a 011. Okay. So at the receiver side, what am I writing? Okay, receiver side. What's the data? 1010 000 and a 011. This was the data, I guess. 011. Yes. Okay. Now let us say that there is no error in the data whenever we are sending. Okay, the data has gone through the physical medium, and whenever the data is received by the receiver, there is no error. Okay, now let us see what happens. Now obviously we have said earlier as well that the generator is common between the sender and the receiver. So obviously the generator in this case also will be 1001, or it can be what? X to the power 3 plus 1, right? And what we will do, we will just start dividing this data with this generator. Okay, so let us see what happens. Very quickly I will divide it. So 1010 000 and a 011. Okay, and if I divide this with a 1001, so it will be 1001. I will be just doing it very quickly. If you don't understand anything, tell me. Okay, so 1 and 0 will be a 1, 1 and 0 will be a 1, this will be a 0, this will be a 0. Cut this off. We will take down this 0, we will take down this 0. Okay, again we will multiply this with a 1, so it will be 1001. So it will be 1010. Cut this off. Take down this 0. So it will be 1001. So it will be 1100. cut this off, take down this 0, and we will take down this 1. Okay, it will be 1 0 0 1, so it will be 0 0 1 0. Cut this off, and we will have this 1, right, and we will have 1 0 0 1, and if you just do the XOR operation, it will be 0 0 0 and a 0. Cut this off. Okay, so I guess you understood what happened. So if the remainder is all zeros, we can safely say there is no error. Am I clear till this? Am I clear, anyone?
Yes, sir.
Yes. Okay.
Yes, sir.
Okay. Now let us say that there is some error. Okay. Now suppose let us say that this 0 becomes a 1. Okay. So now the data will look like what? 1 1 1 0 0 0 0 and a 0 1 1. Okay. Now if I just divide this using the generator, let us see what happens. So if I write 1 1 1 0 0 0 0 and a 0 1 1, and let us divide this using the generator, that is 1 0 0 1. So again we will have 1 0 0 1 initially. So we will have a 1, we will have a 1, we will have a 1, we will have a 0. Cut this off, take down this 0. We will have 1 0 0 1. So 1 and 0 will be 1, 1 and 0 will be 1. This will be 1, this will be a 0. Cut this off, take down this 0. It will be 1 0 0 1. So it will be 1 1 1 and a 0. Cut this off, take down this 0. Again 1 0 0 1. It will be 1 1 1 0. Cut this off. Okay, now we have this 0. The division has become longer. Okay, so it will be 1 0 0 1. So it will be 1 1 1 and a 0. Cut this off. Okay, so we have again this 1. So everything will be 1. So 1 0 0 1. Result is 0 1 1 0. Cut this off, and lastly we will have this 1, right? So I am doing the division here. So 1 1 0, and lastly we will have this 1. So this will be 1, and we will just multiply the generator with a 1. So 1 0 0 1, and what's the result? It is 0 0. This will be a 1, and this will be a 0. Cut this off. Okay, so you can see that the remainder is not all zeros, which means the data has some error and we should reject the data. Okay, am I clear till this?
Yes, sir.
Yes, sir.
Okay, okay then we have completed the error detection part. So error detection had what? 4 things: 1D parity, 2D parity, checksum and CRC. So we have completed CRC till now. Okay, now next we will move to something called as error correction. Okay, so in error correction we will study only one method, and that is known as Hamming code. So don't confuse Hamming code with the Hamming distance. Initially we had studied what Hamming distance, but this is something different, and it is known as nothing but Hamming code. Okay, now so for the error correction part we will study Hamming code, and Hamming code was actually designed for correcting single bit errors. Okay, but Hamming code can also be used for correcting burst errors. There are some other methods as well, but they are not in your syllabus. So we will just study how do we use Hamming code for correcting single bit errors. Okay, now again let us see an example. So suppose the message is 1 0 0 1. Okay, now so this is a 4-bit message, right? Okay, now what do we need to do is, so listen to this very carefully because it may be confusing. Okay, so first and foremost we need to add some redundancy bits, right? Now how do we add this? Let us understand. Now the redundancy bits will be obviously, the number of redundancy bits will be obviously in the form of 2 to the power n. Okay, where n belongs to what? from 0, 1, 2, 3 and so on. Okay. Now, which means if we calculate 2 to the power 0, it will be what? 1. If we calculate 2 to the power 1, it will be 2. If we calculate 2 to the power 2, it will be 4. Okay. Now, we need to understand that if I increase the number of n's and we just make it to the power of 2, whatever be the result should be encompassing the length of the message. Am I clear till this? Did I make sense?
Sir, repeat.
Okay. So which means if we need to add redundancy bits to the data. So how many redundancy bits can we add? So this will be in the form of what? 2 to the power n, where n will belong to a set of from 0, 1, 2, 3 and so on, right? So which means if I just do 2 to the power 0, it will be 1. If I add, if I do 2 to the power 1, it will be 2. If I do 2 to the power 2, it will be 4, right? If I do 2 to the power 3, it will be 8 and so on, right? Now what is this 0? So 0 is actually n, right? What is this 1? It is n. What is this 2? It is n. What is this 3? It is n, right? So n is the number of redundancy bits that we can add. Okay. So if I do 2 to the power 2, which means if I add 2 redundancy bits, right? How many message bits can we encompass? We can encompass 4 message bits, right? If I add 3 redundancy bits, how many message bits can we encompass? We can encompass 8 message bits, right? If we add if I add 1 redundancy bit, how many message bits can we encompass? We can encompass 2 message bits. Am I clear till this?
Yes, sir.
Okay, so which means in our message, if we have 4 message bits, so how many redundancy bits should we add to encompass 4 message bits? We should add 2, right?
Yes, sir.
Okay. Now 2 means not 1 and 2. 2 means 0, 1 and 2, right? That is the reason why I have written this, that n becomes n is starting from 0 till whatever number. Okay. So if I add redundancy bits 2, it means actually we are adding what? 0, 1 and 2, which means actually we are adding 3 redundancy bits. Am I clear? Am I clear to
Yes,
this?
sir.
Okay.
Yes, sir.
Okay. So which means we will add R1, we will add R2 and we will add R0, right? So 0, 1 and 2, we will add actually what? 3 redundancy bits. Okay. Now, where do we add these redundancy bits? Okay. The redundancy bits can be added in power of 2. In power of 2. Just a second, let me check. Just a second. Just a second. Okay, fine. We had a power cut, so okay. So if I just from the current slide, yes. Okay. So in power of 2, okay. So in power of 2, now what is this? The position of R bits. Okay, which means the position of R bits can be from 1, it can be 2, it can be 4, it can be 8, it can be 16 and so on. Am I clear till this? Now we will see how. So is it clear? So whenever we have 3 R bits, so obviously the R bits need to be placed inside the message, right? Now where do we place the R bits in the message? We will place them in positions 1, 2, 4, 8, 16 and so on. Okay. So which means if I have 4 bits like this, so obviously we have 3 R bits. So the first R bit will be at position 1. So suppose we have this as R1, then the second R bit will be at position 2. So if we have R2, the third R bit will be at position 4. So suppose we write this as R4, right? So obviously for these 4 data we will have 3 R bits. So we have we have just settled the position of the r bits. Now, so obviously, if this is 1, this is 2, this is 4, then 3 is remaining, right? So for D3, we can write D3 here. After R4, we can write D5 here. After D5, we can write D6 here. After D6, we can write D7 here. Okay. Now, what is this D3, D5, D6, and D7? These are the data bits, which means the first one is 1, the second one is 0, the third one is 0, and the fourth one is 1. Am I clear till this?
Yes, sir.
Yes, sir.
Okay. Now we need to understand what's the value of this R4, what's the value of this R2, and what is the value of this R1. Okay. Now, to remember this, see, you can remember that to find out the position of R1, what we need to do. To find out the position of R2, what we need to do. To find out the position of R4, what we need to do. You will not find this in a book. So suppose we are creating a truth table. Okay, so we have 3 R bits. So suppose we have R1, we have R2, and we have R4 like this. Okay, so if we create a truth table, so it will be 0, 0, 0, 0, 0, 1, 0, 1, 0, and 0, 1, 1. So 1, 0, 0, 1, 0, 1, 1, 1, 0, and a 1, 1, 1. Okay, now we say that this is 0, 1, 2, 3, 4, 5, 6, and a 7. Okay. Now, for R1, we will just select the datas, the points where the position of R1 is actually 1, right? So again, for R1, we will select what? D1. So if we comprise this of data, so it will be data 1. Next, we will have data 3. Then we will have data 5. And lastly, we will have data 7. Okay. For R2, for R2, we will have the bits or the data points where the value of R2 is 1. So we will have data 2. Okay, then we will have data 3. Then we will have data 6. And lastly, we will have data 7. Right? And for R4, what do we have? We have data 4, data 5, data 6, and data 7 like this. Am I clear? Am I clear till this?
Yes, sir.
Yes, okay. So
Yes, sir.
for R1, we need to calculate the datas, right? So data 1, for data 1, there is no data at position 1, so leave it. For data 3, we have what? 1, right? So if we have 1, so let us write it like this from right to left. So for data 3, we have 1. For data 5, we have 0. And for data 7, we have a 1, right? Okay. Now, if you remember, we had a concept of parity, right? Parity. Now, what's the parity? If we would have followed an odd parity, then we said that if the number of ones are odd, it will be 0. If the number of ones are even, it will be 1. Remember in 1D parity check? Do you remember?
Yes, sir.
Yes, okay. So
Yes,
again, we
sir.
can have a even parity. Okay. So in even parity, what will happen? If the number of ones are even, it will be a 0. If the number of ones are odd, it will be a 1. Okay. So we can write it like this: even and odd. Okay. So let us say, so in the 1D parity check, we had done odd parity. Let us do this with the even parity. Okay. So again, if we see that the number of ones are what? Even. So it will be what? A 0. So R1 in this case will be what? A 0. Okay. For R2, D2 there is nothing. So we have D3. D3 is 1. D6 is 0. And D7 is 1. So again we can see that the number of ones are even. So R2 will be 0. Okay. And lastly we can say that for R4 there is nothing in D4. So D5 is 0. D6 is 0. And D7 is 1. So again we can see that there is a odd number of 1 here. So again it will be a 1. Clear in this? Clear till this?
Yes, sir.
Okay. So R1 in this case, we will just replace this. So it will be a 0, R2 will be a 0, and R4 will be a 1 like this. Okay. Now this is the data that we will send to the receiver side. Okay. How do we send it? We can send it like 1001. This is the actual data, and the redundancy bits we can say it as 1, 0, and 0, like this. This is the data that we will send to the receiver side. Clear till this? Quickly. We have only 10 minutes left.
Yes.
Okay. Okay.
Yes, sir.
Okay, so at the receiver side, let us say that the receiver is receiving this data. So suppose, uh, oh, just a second. Let us add one more slide here. Okay, so from the current slide. Okay, so at the receiver side, suppose what happens. Okay, again, this is not at all practical solution. Just a second. Okay, so at the receiver side, let us see what happens. Okay, so what was the data? It was 1001 and 100, right? So suppose it is 1001 and a 100. Okay, now let us see that suppose this data or this data point, suppose it becomes a 1 during transmission. Okay, so now what will be the data? It will be 1101 and a 100. Now again, when the receiver has received this data, it will understand that these are the 3 redundant bits. So obviously we need to arrange the redundant bits in the message bit. Okay, so what we will do, it will write 0, 0, 1, and this is the 1, this is the 0, this is the 1 and a 1. Okay, so this is the R1, this is the R2, this is data 3, this is R4, this is data 5, this is data 6, and data 7. Okay, clear till this?
Yes, sir.
Okay, now the receiver, what it will do? It will just calculate the values of the redundant bits. Okay, now let us check. So for R1, it was 0, right? And for R1, what did we have? We had D3, D5, and D7. So we had 0. D3 is what? 1. D5 is what? 0. And D7 is what? 1. Right? So if you remember, in the sender case, we wanted to find out the values of R, right? Right? But in this case, we already have the value of R, right? So again, whenever we will calculate the parity, we will include the R bit as well to calculate the parity, right? Clear till this?
Yes, sir.
Yes, sir.
So for one, so we can see that there is what? How many number of ones? There are even number of ones. So obviously it will be a 0. Fine. Okay. For R2, let us see what happens. So the value of R2 is 0. And for R2 we had D3, D6, and D7. So D3 is 1. Alright. D3 is 1. D6 is what? 1. And D7 is what? 1. So we have odd number of 1. So this should be a 1, right? Okay. And for R4 we had 1, right? So we had a 1, and for R4 we had D5, D6, and D7. So D5 is what? 0, D6 is what? A 1, and D7 is a 1. So again we have odd number of 1, so this should be what? 1. Okay. Now, so if I just write it like this, R4, R2, and R1, we have what? 1, 1, 0. Now what is this 1, 1, 0 in the truth table? Let us understand. So this 1, 1, 0 is what? 6, right? So this means 6. So this means, where is the error? It is in the 6th bit, right? So if you remember, I just changed this 0 to a 1. Now what is this 0? What is the position of this? It is at this position, right? So we can safely say that the error is at what? The 6th bit. And if the error is at 6th bit, then we can safely say that if I change this 1, if I change this 1 into a 0, the message will become what? 1, 0, 0, 1. So now the message will be corrected. Am I clear?
Yes, sir.
Everyone?
Yes, sir.
Okay.
Yes, sir.
Okay.
Yes, sir.
Okay. Okay. So in your questions, what can come? The questions can come like this. So it can say that we have a 7 cross 4 scheme, right? Where the data will be given. Suppose the data will be given as 1001 and 100, right? So again, you will need to understand what does this 7 cross 4 scheme mean. It means that 7 is what? The length of the code word. Length of code word is what? 7. Okay. Length of message is what? 4. Okay. If you do you remember what is code word? We have a data word. If we add redundancy bits to the data word, it becomes a code word. You remember?
Yes, sir.
So again, how many redundancy bits are there? So 7 minus 4, it will be 3. Okay. Now it can be given like this, 7 cross 4 scheme, and the data will be given. Again, if the data is given like this, you can understand that if this is a message of 4 bits, so the first 4 bits are the message, right? And the redundancy bits are what? 3. So the next 3 bits are the redundancy bits. So you can see it like this. Okay. Also in your question, it may be given that it is using a even parity or a odd parity. So it will be given. Okay. Now again, if you remember, if it's even parity, if the number of ones are even, number of ones are even number of ones, it will be a 0, and if it is a odd number of 1, it will be what? A 1. For odd parity, if the number of ones are odd, it will be a 0, and if the number of ones are even, it will be a 1. Clear till this?
Yes, sir.
Okay, it's already 10:15. I don't think we should move ahead with the flow control. Let us do the flow control in the next class. Okay. So let me save this first. Okay, we will keep this. Okay, and I will share this PPT with you all. So again, looking at the PPT, looking at the video presentation as well, you will be able to understand everything. Okay. So let me just stop my sharing first. Okay. Okay, and also do you have the IMCRP exam code? Just a second, I will give it to you in the chat box. Just a second. Okay, so this is the exam code I've given in the chat box. Okay, so again, the exam is valid till 10:30. If you are facing any issues with the exam, contact me before 10:30. Don't contact me after 10:30 because I won't be able to do anything. Also, if you do not have problems with today's class, you can leave the meeting and give the exam. If you have issues, stay back in the meeting. Tell me what's the problem. I will try and solve it. Okay. Thank you.
Thank you, sir.
Yep.